All right, now we have oscillations in an LC circuit. Okay, this is actually really cool stuff. So, in my, professional and geeky opinion, we're going to just draw a special circuit here where we have an EMF, a resistor, no, sorry, I don't want a resistor there. I want a capacitor and an inductor. All right. And here we have a switch. And no, I'm putting it in the wrong place. The switch isn't there. Okay, I do this every single time. The switch is not there. It doesn't want to go away. The switch is here. All right, so when we start, we start like that. Okay? Uh-oh. Okay. We start our switch, and when we close the switch, what happens? We sit there for a while, and we wait, 5 tau, 6 tau. Okay. What is the current in our circuit? If this is closed on the outside, what is the current in this circuit? After a significant period of time. Okay. What does this do for us? This will reach a maximum amount of charge, right? Okay. Will charge flow across that capacitor once it reaches the maximum flow of charge? No, it does not. We do not have a disastrous short circuit across our capacitor. Okay. The current after a long period of time of anything with a capacitor in it is 0. The current stops. Yeah, that's ringing a bell? Hopefully it's ringing a bell. All right. So once this happens and the current stops, we have potential energy stored in, all right, hold on, this is our E, this is our resistance, this is a capacitor. There we go. We have energy stored in the capacitor, and we also have energy stored in the inductor, and that all together is going to equal our total energy that's stored in the system. That's stored in the system, because both of these store energy. Okay, a capacitor stores energy in the electric field, and our inductor is going to store energy in magnetic field. Yeah? Okay, so we have that. Now, what happens when that switch isn't there anymore? It's here. Does the current go through the voltage source? Does the current go through the resistor? No. So all we have is this LC circuit. And we have energy stored in the inductor, and we have energy stored in the capacitor. What happened before when we had an RC circuit? What did the capacitor do? It started to discharge, right? And essentially created a backflow of current going the other direction, right? But what happens with the inductor when that happens? Okay, our current starts going the other way, but that means we start having this change in current, right? And that creates and the inductor doesn't like that, so it starts, so it's back off, and it starts creating a voltage that's going the other direction, right? Okay, so as the capacitor discharges, it starts to create a magnetic field in the inductor until, but as it's doing that current, it doesn't like a change in current. So the current is changing. This wants it to stay the same. No matter what it is, it doesn't matter what the current is, it just wants it to stay the same. Don't change the current until this capacitor completely discharges. Well, if it completely discharges, it's at 0, right? But the inductor doesn't want the current to change. So what does it do? It keeps the current the same. Even after this reaches 0 charge, the current stays the same. And it reverses the charge on the capacitor. So if it was once positive across here, negative, 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 it doesn't stop once it's discharged. It reverse charges it the other way. So all of a sudden, this is negative, negative, negative. This becomes positive, positive, positive. And it goes all the way around the other direction because it doesn't like a change in the current. It wants to keep shifting the charge when the capacitor discharges. Which means that if it keeps going, what does it do to the capacitor? It recharges the capacitor again. So if the capacitor recharges, then it's going to go back and it's going to discharge, and the same process happens, and so you start getting, so it reverses polarity on the capacitor in this circuit. And it keeps going back and forth by reversing polarity on a capacitor. You have seen this behavior before. Okay, so all the energy is stored in one place. Then when it gets down here, it's stored in the other. When it gets over here, it's stored in the other place. Potential energy, kinetic energy, potential energy, right? Okay, well, now we have two different energy sources that are competing with each other, for our total amount of energy, because the sum of these actually equals 0. Oh, I'm sorry, the change in the total change in them equals 0. We still have the law of conservation of energy. Okay, so because of this, we have UC plus UL equals our total U. All right, what is the potential energy stored in the capacitor? Q squared over 2C. Total energy stored in an inductor from just a few minutes ago. Okay, and that equals our U, and if we do that to it, check this out. This becomes Q over C dq dt plus Li di dt equals 0. Yeah? Guys following there? Okay. If we divide both of these, well, this is di dt, right? What is dq dt? dq dt is our current, right? So if we divide both of these by I, that's going to cancel, and that cancels. Right? So we're left with Q over C plus L di dt equals 0. Well, I'm going to move over here for more room. This becomes, where are we? I'm going to skip a little step in algebra here. But I'm going to isolate di dt is going to equal negative Q over LC, right? But what was current again? Current is dq dt, right? But this is, so this is d dt of dq dt. Uh-oh. This we have seen before. We have seen this before. We have seen this with
Oscillations.
Remember that? With springs? Okay, or G over L for pendulum? Yeah? Right, G over L? Yes. This L over C is omega squared. Okay, and sure enough, if you were to measure Q versus time, the charge on the capacitor per any unit time, it looks like that. So our Q over T becomes, I'm sorry, okay, whatever our max charge is, cosine omega T. And our period is going to be that. So there are your oscillations, Nick. Capiche? Okay. And that are your oscillations in an LC circuit.